All right, in the previous lesson, we were working on getting the area of a triangle that did not contain a right angle. And so we're going to continue to work on triangles that don't contain a right angle. Those are known as oblique triangles, whether they're obtuse or acute. If they don't contain a right angle, they're called an oblique triangle. And so we need another way to solve the triangle that doesn't have a right angle because SOHCAHTOA doesn't apply and neither does Pythag. So we come up with a different way. So the triangle that you see below here is just a generic triangle ABC. And we can use the area formula to express the area of this triangle in three different ways, because what we know about the area formula is that it requires an angle, and so we can use any of the three angles as that input angle. So if I use angle A, then x and y would be the two sides surrounding angle A, and I would have 1/2 BC sine A. If I use angle B, well, then I have 1/2 AC, because from angle B, A and C would be the surrounding sides. And if I used angle C, I'd have A and B. So there's three different ways I can write it. It asks me to write an extended equality with more than one equal sign that relates these three expressions. Well, since they're all the same triangle, all of their area formulas should be the same. So if I set each of the three area formulas equal to each other, I get this extended equality. And then it's asking us to divide each side of this equation by 1/2 ABC. And that's kind of an algebra trick that's being done here. So you just bear with me for a second. If I divide each of these by 1/2 ABC, and just set that up on each one, 1/2 ABC and 1/2 ABC. In the first one, the 1/2s are going to cancel each other, the B's cancel each other, and the C's cancel each other. And so all I have is an A in the denominator. In the second one, I cancel the 1/2s, the A's and the C's, and there's just a B in the denominator. The third one, I cancel the 1/2s and the A's and the B's, and so there's just a C in the denominator. So each one of these fractions has been reduced to the point where it's sine of an angle over its opposite side. So sine of A over little a, sine of B over little b, sine of C over little c. Any two of these ratios can be used together, and that's the law of sines. Sine of an angle in a triangle is divided by its opposite side, and that ratio is equal to the sine of any other angle divided by its opposite side. You could also put the side lengths on top, but typically you will see it with the sines of the angles on the top and then the side lengths on the bottom. All right, so as an example of this, we have triangle ABC shown here. We've got our three angles filled in. The thing to note about the law of sines is you always need to be doing an opposite crisscross relationship. So if I'm trying to solve for AB first, I'm just going to put an X in that spot. And then I can take the 68 and go across to there. And so the 80-degree angle goes with the 16 length side, and the 68-degree angle goes with the X length side. So using the law of sines, if I say sine of 80 over 16 equals sine of 68 over X, then I will be able to solve that equation, figure out what X equals. But no, it is the law of sines. So one mistake that people sometimes make is they just put 80 over 16 and 68 over X. That's not how it works. It's not the angle, it's sine of the angle that needs to be used in this formula. All right, so to solve this, if I do a cross product, I have X times sine 80 equals 16 times sine 68. So if I divide both sides by sine 80, I get X equals 16 sine 68 divided by sine 80. All right, so when you put that into the calculator, the one thing you have to be very careful about is that you need to close those parentheses on the 68. Otherwise, the calculator is going to think that you're dividing by sine 80 within the angle. You got to close off the angle, then divide by sine 80. As you enter this into the calculator, you should get approximately 15.1. So that would be segment AB. All right, and then I can just use a different variable for AC. If I use a y there, now to crisscross, I'm going to use this 32-degree angle to connect to the y. And we'll go sine of 80 over 16 again, because I do want to use given information rather than the x I just got. And we'll make that equal to sine of 32 over y. And so I can just calculate this one the same way. Y sine 80 equals 16 sine 32. And so y is equal to 16 sine 32 over sine 80. And again, being careful to close those parentheses before dividing on the calculator, I get approximately 8.6 for that side length. Okay, so law of sines is fairly straightforward to use as long as you can pair up a known angle with a known side and a known angle with an unknown side. Then we can make that proportion and solve it. All right, on the next page. So I've got a triangle with a 45-degree angle and a 30-degree angle. I think in this one it's going to make sense for me to solve for this third angle. So let's do that first. And let's 45 and 30, that's 75, so this is going to be 105. I always want to know what all three angles are just in case I need them. Now in this one I'm solving for DF, so I'll put my X over here, but had I needed EF, I would have needed the 105. So it's just a good habit to be in, is to fill in any missing angles. So law of sines is going to allow me to take the 45 and pair it with the X, take the 30 degree and pair it with the 20, and we have a crisscross, so we're able to use a law of sines here. So if I go sine 30 over 20 equals sine 45 over X, that sets it up with these crisscrossing connectors. So X times sine 30 equals 20 times sine 45. And so I just divide, I get X equals 20 sine 45 over sine 30. That's the exact answer because no trig has been entered into the calculator. So this would be the exact answer. The approximate answer would come out to about 28.3. After putting all this into the calculator, we get about 28.3. And so we've got that one solved. Okay, now this does say something about simplest form too. So I just want a quick touch on that here. Let's say I had not used the law of sines. So if I just erase all these markings and I'm interested in X, because of the 45-degree angle here and the 30-degree angle here, what if I had just dropped an altitude straight down and made a right angle there? I could have solved for this height because it's a 45-degree right triangle, so there would be another 45 here. So I could just divide 20 by root 2, and that's my height. So 20 over root 2. And then that's my short side, right? Across from the 30-degree angle. So to get to the hypotenuse in a 30 to 60-degree triangle, I just multiply by 2. So 20 over root 2 times 2 is equal to 40 over root 2. And then I can just multiply by root 2 in both positions to simplify further. So I'd have 40 root 2 over 2, which is equal to 20 root 2. So that's another way to think about it in simplest form, is using my special right triangle techniques. This is my trig form, and this is my 30-60 form. All right, exercise 4. So I'm looking for angle I. So I'll put a little theta in that position, my angle variable. And I know that these two sides are 12 and 26. Angle H is 25, so all that's already been entered for me. All right, so the law of sines here says that I can connect the 25-degree angle over to the 12, and the theta connects to the 26. There's my crisscross. Let's set up law of sines. So sine of theta over its opposite side 26 is equal to sine of 25 over its opposite side 12. All right, so I do my cross multiplying. I have 12 sine theta equals 26 sine 25. And I need to get theta by itself. So first let's get sine theta by itself. So it's 26 sine 25 over 12. So I need an inverse now. Theta is going to be equal to inverse sine. And I need to put this entire fraction in as my input for the inverse. So 26 sine 25 over 12. And once again, be careful. You close your parentheses on the 25. We don't want this angle to be 25/12ths. We want to do finish the numerator first and then divide by 12. So theta in this case comes out to about 66.3 degrees. Now, there is something about using the law of sines in an SSA triangle like this. This is an SSA labeling, which is different from what we've seen before. When I'm solving for a missing angle, it's possible that that angle is the obtuse version or the acute version. As you can see, the way it's drawn here, This is the obtuse version. So to get the obtuse version, what I need to do is subtract 180 minus 66.3, and that would come out to 113.7 as my alternate angle for theta. Here's the reason why. Because of the SSA relationship, because this angle is not locked in, and neither is this one up here at J, this 12 could be swinging out this way too. And this is why SSA was not a valid congruence statement back when we were studying congruence, because there's not a unique triangle that 12 creates. That 12 could have been out here, and this theta then would be an acute angle. So it could be acute, could be obtuse. Now I just want to check it and make sure, because if this was 113.7 and this is 25, that's still under 180. So there would still be some degrees left over for angle J. So you do have to check that just to make sure. But if it's 66.3, it would look more like this larger triangle, and then I'd have a bigger angle up here at J. So if we're solving for an angle with a lot of signs, we could get more than one answer. All right, exercise 5. So we've got everything filled in here. You are going to have to draw these diagrams. Pardon that pop-up there. You are going to have to draw these diagrams on your own as well from time to time, so just want to be careful that it's labeled exactly as it says. So I've got everything filled in. I want to know the length of AB, so let's put an X in that spot. And this X is actually part of a right triangle. And I actually do know one of the angles in that right triangle too, because it's a linear pair with 115, so I know that this is 65 degrees. So if I knew either BC or AC, I could just use trig, could just use SOHCAHTOA to solve for X. I don't yet, but I have a way to get it because I have two angles in this obtuse triangle and I have a side length here. So as I said at the beginning of this, let's be in the habit of completing whatever triangles we can. I have 115 and 20, so that adds up to 135, which means there must be a 45-degree angle up here. And this 18 then the 45-degree angle would connect to the 18 if I'm interested in law of sines. And I am, because if I can figure out AC, then I can solve this triangle over here. So let's connect the 20-degree angle to here and call that y. Because if I can solve for y, then I can just use a regular sine equation to solve for x. Okay, so law of sine says we're going to put sine of 20 over y, because those are connected, and sine of 45 over 18, because those are connected. All right, so my y is going to equal the cross product 18 sine 20 divided by what would be attached to the y, which is sine 45. Just taking a little one-step shortcut there. 20 gets parentheses. When I put that into the calculator, y comes out to be approximately 8.7. So that's over here. And now that acts as the hypotenuse of triangle ABC. And the x would be the opposite in triangle ABC from 65 degrees. So that's a sine equation. Just going back to SOHCAHTOA now. So sine 65 is equal to opposite x over hypotenuse 8.7. And so x is 8.7 times sine 65. And so x comes out to about 7.9. And that is AB. Now this direction said you will need to apply the law of sine twice. We didn't need the law of sine the second time because once we got to the right triangle, we were good. If we had a second oblique triangle here, like say this AB segment came out this way, then yeah, I'd want to use the law of sines a second time. I need to know another angle, but I would want to do that. But anytime you can use a right triangle in its strategies, you should.